Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, string transformation. The problem is very interesting and a bit hard as well, as you can see from the submissions itself. So, we'll be looking at how exactly to approach this problem, and as it is a bit hard, it involves some mathematics, so you have to pay some attention, and at times you have to pause and think to understand the proof that is explained. So with that, let's get started. The problem states that you are given two string s and t of equal length n, and you have to perform the following operation on string s. The operation is you will remove a suffix of s of any length l from 0 to n and append it to the start of the x. So for example, if s is a, b, c, d, in one operation you will remove the suffix cd and you can append it to the front. So the resultant string would become cdab. You are also given an integer k and you have to return the number of ways in which s can be transformed into t in exactly k operation. So you have to perform k operation, that is you have to select a suffix of positive length and append it to s exactly k number of times, and finally you have to arrive at t. So as there are multiple possible ways to achieve t from s, you have to return the number of ways to do that. As the number of ways can be huge, you have to return its modulus 10 to the power 9 plus 7. So let's just take one example. Let's say s is abcd and t is cdab and k is 2. Basically in exactly 2 operation you have to convert abcd into cdab. So in first operation you can choose the suffix from index 3, and if you choose this, the resultant string would become dabc, and then you can choose again the suffix with index 3. So if you choose the suffix in index 3, this time it will be c, so the string would become cdab, and cdab is equals to cdab, that is t. So this is one way. Another way could be you start from suffix with index 1, so bcd, and append it to s. So bcda would be the resultant string, and again you start from index 1 and the resultant string would be cdab, which is equals to t. So you can try other combinations, and there are no other combinations in which you will be able to obtain t from the given string s in exactly 2 operation, and hence the answer here is 2. So hope the problem statement is clear. Now how to solve this? So let's assume that this is our s and this is our t. Now notice the operation. The operation states that you will be removing a suffix of s and appending it to s. So this is nothing but the rotation of string s itself. So whenever rotation is involved, the common trick is to just have the string appended 2 times. So you will just replicate the string s 2 times, and now this resultant string would have all possible rotation. So this is one possible rotation, right, which is the original string itself. This is another possible string after rotation, which is if you rotate at b, so this will be the string you will be getting, b a b a b a b, and similarly this is another possible rotation which is obtained after 2 rotation, and so on and so forth. So with this strategy you will get all possible rotation of s. Now your final destination should be one of these rotations. If t doesn't match with any of these rotations, you can't found t no matter what, right? Because with the given operation you can only rotate. That's the only thing you can do. So the simple strategy could be just take t, right, and see where it is matching, right? So in this case we can see this is one possible match. So we will start from this. Is it matching? No. We'll see this. Is it matching? Yes. So because it is matching, it means if we rotate one time, we will be able to convert the given string s into t. So in one rotation we are able to reach our destination. But if you remember, we have to perform exactly k operations. So what we need now is we need k numbers which if we sum and take modulus n, this entire thing would give us this number, right? If we are able to obtain such series of k numbers, we will be assured that after applying these series of rotations, at the end it would translate to just one rotation, and after one rotation we are sure that s will be equals to t, right? So that's the basic idea. We will cover what all rotations will give us the final destination t, and for each of these rotations we will try to figure out how many such sequence of numbers exist, such that if we sum them up and take modulus n, it will give us the same it will give us our target number, let's say p, right? Now in this particular example, let's just complete this example. So in this case we have to find out k numbers, series of k numbers, such that if we sum it will be equivalent to 1. If let's move forward, so this is not equivalent, let's move forward, this is equivalent. So again it will, what it means, it means that if we figure out a series of k numbers such that if we sum them up it will give us 3, then also s can be converted to 3, right? So this is another possible solution. Now this one and finally this one, this is also matching. So again we have to figure out the series of k numbers such that if we sum them all up and take modulus n, they will give us 5, right? So let's say there is x1 ways to achieve 1, like there is x1 number of sequences of number which if we sum up will give 1. There is x2 number of such sequences of number which if we sum give 3. There is x3 number of such sequences which will give us 5. So the final answer would be x1 plus x2 plus s3, right? So that's the basic approach that we will be trying. So in all this approach, the common part is, given a number, give us all the possible k sequence of numbers which if we sum will give us that particular number p. So that's the problem we will be trying to solve next. Number of ways such that x1 plus x2 all the way up to xk modulus n is equals to a given constant t. So this t is constant, right? Now how to actually solve this particular thing? So let's say FIR denotes the value or the number of ways in which I will get a remainder of r, or basically this r is equals to t here, a remainder of r if I will be adding I numbers, right? Now you are saying is we are adding I numbers, right? And we are getting a remainder of r. Now what you can do is, okay, what will be this number? What's the first number? First number could be anything between 1 and n minus 1, right? So what you can say, okay, first number could be either 1, 2, all the way up to n minus 1, right? So what is the value of FIR? FIR would be Fi minus 1 r minus 1 modulus n. Basically the number of ways in which I can fill I minus 1 numbers, or I can get I minus 1 numbers such that if we sum them all up, the remainder is r minus 1 modulus n, right? Similarly, if I put 2 here, then what I need remaining r minus 1 or remaining I minus 1 numbers to have a remainder of r minus 2. Similarly, if I put 3 here, I want the remaining I minus 1 numbers to sum equals to 3, and all the way up to, if I put n minus 1 here, then I want the remaining sum to be equals to r minus n plus 1, right? So this is what we finally want. Now you can solve this recurrence and you will get the answer. So this recurrence is equivalent to this summation, right? F of I minus 1 comma r minus x modulus n, where x is between 1 and n minus 1. Now look at this closely. What exactly this means? So this means you have r here, right? You have 0 here and you have n minus 1 here. So you have some numbers in between, right? Now what you are saying is I will subtract x. Now x lies between 1 and n minus 1. So if I subtract 1, I will get this number. Subtract 2, subtract 3, all the way up. If I subtract r, I will get this number. Now if I subtract r plus 1, I will get this number, r plus 2, r plus 3, and finally if I subtract n minus 1, I will get this number. But so what is the value? Value is the summation of everything except r, right? So that's what we have done. The value is now summation of everything from 0 to n minus 1 except the current value of r, right? Now from here the solution is very straightforward. I would strongly encourage you to pause and try to solve after this by yourself. So hope you have thought about it. The solution is now, we arrived at this particular recurrence relation. We just replaced this entire expression of summation of x equal to 0 to n minus 1 f of I minus 1 r minus x with just f of I, right? So the recurrence relation can be said as f of ir is equals to f of I minus 1 minus f of I minus 1 comma r, right? Now let's just sum this entire thing up. So this is like basic 11 or 12 class mathematics. We will just sum this entire thing up for from 0 to n minus 1. So if you sum this f of ir from 0 to n minus 1, what you will get? You will get f of I minus 1 n number of times, right? And you will get f of I minus 1 comma 0, f of I minus 1 comma 1, f of I minus 1 comma 2, all the way up to f of I minus 1 n minus 1, right? So this is what you will be getting if you just sum all the values of f of ir. So if because you are summing all the values of f of ir, this will also be converted to capital F, right? Now what this thing is, this is nothing but f of I, right? So we will simply replace this with f of I minus 1, capital F of I minus 1, and this entire expression would look something like this, right? Now you can simply apply this exact same recurrence for f of I minus 1 as well, and you will get this particular thing. Basically f of I minus 1 will be equals to f of I minus 2 multiplied by n minus 1. So this will become f of I is equals to f of I minus 2 multiplied by n minus 1 whole square. If you keep on doing this, you will finally end up at f of 1 multiplied by n minus 1 power I minus 1. Now why I minus 1? A simple way to look at it is whatever minus was there, that was the power. So if you think this, what you will subtract with I so that you will get 1, I minus 1, right? So that's the power. So finally we get this particular recurrence relation. Now what will be the value of f of 1? If we are able to find this, we have find f of I, right? Now f of 1 will simply be f of 1 0, small f of 1 1, small f of 1 2, so all the way up to small f of 1 n. What is f of 1 0? If we just read it loud, f of 1 0 is number of ways in which I can sum one number such that I will get 0. So what you are saying is, I have just one space, I can fill this space with anything between 1 and n minus 1, and I want the summation of this number to be equals to 0. Basically you can put anything between 1 and n minus 1 and you want 0. Not possible, right? So this value would be 0. Similarly, this denotes I have one space, I need to make a sum of 1. So this is possible because you can actually put 1 here, right? So the value of this would be 1. There is just one way. Similarly, all other thing, the value would be 1. So the final output of this would be n minus 1. Only f of 1 comma 0 would be 0. Now if you just substitute f of 1 here, this entire thing would become f of I is equals to n minus 1 to the power I, right? Notice we just find out capital F of I, but we actually have to find out small f. So this finding out small f is relatively straightforward. This was the recurrence for small f, capital F of I minus 1 minus small f of I minus 1 comma r, and this is what we have just find out for the capital F value, right? Now if you simply expand this further, what you will get? You will get very similar thing. You will get n minus 1 power I minus 2 minus f of I minus 2 comma r. So you will simply have this formula, and if you continue expanding this further, at the end you will be getting f of 1r with either plus or minus. This depends how much number of expressions you have. If you have odd, you will get plus, otherwise minus. So it actually doesn't matter, we will look at it, but for now this is the base case that we need to solve. Now what will be the value of f of 1 comma r? What is f of 1 comma r? F of 1 comma r is, again, if I have just one space and I need to make a sum of r, then how many ways are there? So this is exactly what we have discussed before. So only f of 1 comma 0 would be 0, all other things would be 1, right? So this recurrence relation would be evaluated to these two p's. If r is 0, then you will have 0 at the end. If r is anything else, you will have 1 at the end, right? So if you look closely, this is what we wanted, and this exactly is a geometric progression, nothing else. And we already know how to solve or how to find a sum of a GP, and you can simply evaluate this thing with a GP formula, and you will be able to find out what is f of I comma r efficiently. So this I in our case is simply k, and r can be either 0 or anything else. If it is 0, it will end with 0. If it is anything else, it will end with 1, right? So for simplicity, what we will do, we will simply put this 1 and finally add or subtract 1 at the end, right? So this is what we would be doing, and the summation of this GP would be simply a r power n minus 1 minus a divided by r minus 1. This is what the summation of a GP is. This is the n plus 1th term, and this is the first term, right? So if you just just put the values here, you will get r in this case is 1 minus n. So what we will get a we will get n minus 1 to the power I or to the power k if you want to find f of k, minus 1 to the power k, right, divided by 1 minus n completely, because this is just if you know, like if the summation is decreasing, the formula usually we just do this thing 1 minus r. So 1 minus n would be n, right? So this is how it would look like. Now you can simply do this, and if the value of x is 0, you will simply add back or subtract back 1 based on what the value we have here. So what the value we will have here, it's simply minus 1 to the power k, right? So this is how we will find out the number of ways to actually get k numbers, such that if you sum them, you will be ending up with a particular digit t, right? And this is how the entire pseudo code would look like. What you will do, as discussed, you will simply try to let's just quickly look at that once again. So you will simply try to match t with the existing r. Whenever it matches, we will get a particular value of p, and we will find the value of f of k of p for all such p, right? So all the value of p you will get by doing this, and you will just sum the value of f of k comma p for all such p, and the value of every f of k comma p will be equal except when p equals to 0, and for that we discussed what changes we need to do. So that's a simple algorithm. The only thing you need to now take care of is this string matching. If you do this string matching naively, this will lead you to order n square solution. So better to use any string matching algorithm like Z algorithm or Rabin-Knapp. If you don't know any of these algorithms, you can just simply use hashing. You can just hash this entire string, and whenever you are comparing, you can simply calculate the hash of this thing. How you will do this? Prefix sum. You will simply maintain the prefix sum of everything. Now the prefix sum of this thing would be simply be prefix of this minus prefix of this. So you will get the exact hash of this particular string. You can simply compare the hash, and if the hash is equal, the strings are equal. Once you found this particular value of p, you can sum all the value of p, and that will give you your final result. So I am not showing just the code for this. The code would be very interesting to write. So I would strongly encourage you to try coding this entire thing by yourself and get it submitted as well. So I will link the code that I have done in the description down below, so that you can refer if you want. But again, I would encourage you to code this entire thing by yourself. If you have any doubts, feel free to post them in the comment section below. I would be able to answer. And I hope you learn something new. I will see you in the next one. Thank you.